Our next speaker is Adriana Ferreira. She joined the Air Center as a project developer following the completion of her PhD in surveying engineering at the Faculty of Sciences, University of Porto. Her work has primarily focused on ocean applications with particular expertise in sub-mesoscale processes such as short period internal waves. Adriana's research combines satellite observations, in situ data, oceanographic models, and more recently, machine learning techniques to advance understanding in the field. Adriana.
So good morning. I'm here to present the internal wave service that was presented for the first time last year in Julia EO 25. So a small introduction about what are ocean internal waves. Internal waves are waves that propagate inside the ocean between layers of different density, not on sea surface as we are used to see. This occurs because as we go deeper into the ocean, the water becomes denser. When the density changes sharply due to the temperature or salinity, it creates a boundary called the peak-knock line. When this interface is disturbed, typically by underwater topography, such as seamounts or continental shelf edges, internal waves are generated. The movement of internal waves generate orbital particle motions which, at the sea surface, form slick bands of roughness and smoothness that make them visible both to naked eye and in satellite data. The strongest type is called internal solitary waves and can reach amplitudes of hundreds of meters, transport energy efficiently without dispersing, and generate strong currents often bigger than 2 meters per second. Here we have a photograph of the sea surface with an internal wave in Cape Cod. And here we have a satellite image from MODIS with an internal wave that we can see in the signature in the sea surface in Gibraltar Strait. But why are they important? We can split in two big different areas: natural processes and anthropogenic activities. In natural processes, internal solitary waves transport energy, they contribute to mixing, transport nutrients, help in climate regulation, so they have a connection with global ocean circulation. In anthropogenic activities, they also make infrastructure and coastal impacts and influence engineering and submarine operations. Here we have 3 images representing 3 key studies of internal solitary waves. The first one, it's a recent study about the importance of internal solitary waves in climate. The second image, it's about a study done in 1970s where Osborne and Birch suggested that unexplained movements in oil platforms were caused by internal waves. At the time, the idea was dismissed as speculative and Osborne was removed from the project, but years later, satellite data confirmed that they were right, and nowadays we know that is an important factor to these structures. The last image, it's about an Indonesian submarine that sank during a training exercise in 2021. Although the cause was never confirmed, some scientists suggested that large internal solitary waves up to 100 meters in amplitude observed in the area contributed to the accident by affecting the submarine stability and buoyancy. So, the problem. Global observation remains challenging and has been restricted to a few hotspots. This was the most up-to-date map of internal waves that we were aware of. It was created using satellite images, MODIS, that are optical images, from August 2002 to May 2004. This is the map that even nowadays the researchers use to know the hotspots of internal solitary waves. And I take the opportunity to show that, for example, to the east of 115 degrees west, we almost don't have internal waves. We have just 4 random points here. Also in Southern Ocean, we don't have internal waves, and we have very few internal waves here in the equatorial Atlantic Ocean. But now we believe that we can build a current involving map of internal waves with improved coverage, resolution, and near real-time potential. For example, using Sentinel-1 satellite images since 2014 and ongoing. Here we have some examples of internal solitary waves in optical images in Sentinel-2, Sentinel-3, and MODIS images. However, can be very difficult to detect due to the atmospheric conditions, especially the clouds, and also the sun glint. Here we have some examples of SAR images. The first one is a CSAT image in 1978 in the Gulf of Mexico. The others are the Sentinel-1 images in other locations. So our main objective is to create the first global near real-time service for the detection and monitoring of internal waves. Our goals are support researchers, consolidate internal waves as mainstream, and find end users beyond researchers. How we have created the internal waves service. For now, we are using the wave mode Sentinel-1 images that are available mainly in open ocean. They have 20 kilometers by 20 kilometers in size, and here we have some examples of images with internal waves and not internal waves. This is our current pipeline, so every day the model processes all available Sentinel-1 wave mode images that are thousands per day. Images classified as negative are automatically discarded, while potential positives are currently reviewed by experts and labeled as confirmed positives, confirmed negatives, and inconclusive. The newly validated cases are continuously used to retrain and improve the model with long-term goal of reaching full automation, eliminating the need for manual validation by the expert. Confirmed positive detections are published on an open access global map. NVIDIA supported us in developing a robust machine learning model for this application. This is our validation platform, which now includes 2,437 confirmed positive cases. Initially, the model's performance was not very strong, which is why we had a large number of confirmed negatives, almost 17,000. Right now, however, confirmed negatives are really rare. On the right, we can see an example of an internal wave image in Atlantic equator that was predicted as positive by the machine learning model and then confirmed as positive by the expert. In our machine learning model to do the training, we are doing augmentation in the confirmed positive cases. For now, we don't need to do augmentation in negative cases because we have a lot of cases. Which machine learning model do we use? We are still using the machine learning model developed by Gilberto Titorix as part of a competition we launched on the Kaggle platform, which has shown very strong results. The model has since been retraining using the new cases we have collected. This is our current map of internal waves. At its stage, it includes approximately 1 year and a half of data worldwide and 5 years and a half data in equatorial Pacific Ocean. We can already identify some known hotspots. Just to say that the color scale represents the number of overlapping detections. And we can see some known hotspots like in South China Sea, in Mascarenes Ridge, the Amazon Shelf, and the Bay of Biscay. But we can also already identify some new or unexpected regions when we compare with the map that I showed before, like sectors of the Southern Ocean, tropical Atlantic near West Africa, and Central and Eastern Equatorial Pacific, mainly between 8 degrees and 10 degrees north, where we can see a strict line around these latitudes. To the best of our knowledge, this is the most up-to-date and representative map of internal waves in the open ocean worldwide. This is an example of a persistent internal solitary wave activity in the Gulf Stream. In 13 months, we have 12 different images with internal waves. We can see that even when the signature in the surface is weak, the machine learning model can detect the cases. This image is published in a conference paper we had in a SPY conference. With the goal of improving this prototype, we built a community around the service. To this end, we organized the Internal Wave Service Workshop in April 2025 here on Terceira Island, where we discussed the current needs and the next steps for the initiative. We brought together experts in theory, modeling, Earth observation, and missions, which led to very valuable outcomes. The next Internal Wave Service workshop will be in April in Lisbon from 14th to 16th April. Please let us know if you would like to join us. George, who is present here, participated in the workshop, as we can see in the photograph next to me, as well as Manuela Juliano and Gail, despite not being in the photo group. Thank you for your contributions. We could also, we had the pleasure of publish in a paper about this workshop in the Bulletin of the American Meteorological Society. Since the last Julia EO that we consider the beginning of this initiative, we have grown steadily and now we collaborate with more 23 institutions in 12 countries. And as next steps, we would like to expand and curate a global internal solitary wave dataset from Sentinel-1 wave mode images since 2014 and ongoing. Integrate IW mode data from Sentinel-1 to increase spatial coverage, especially in coastal areas. Develop internal solitary wave segmentation methods for precise localization and extraction of physical parameters. Prepare for data simulation of future missions, especially ROSEL, that will be launched in 2028. Explore synergies between SAR and SWOT observations to estimate, for example, internal solitary wave amplitudes, especially in key regions like Amazon Shelf and Banda Sea, where the amplitudes are large. Establish thematic working groups focused on data curation, AI model development, and science applications. For that, we applied for a cost action that would be great for this. Support collaborative publications and plan follow-up workshops in April 2026, as I showed before. leverage AI to revisit archived data, for example, ENVISAT or ERS, before of 2014, and align with Copernicus program evolution. And that's it. Thank you.
There's a question, there's some.
Ah.
Hi. Thank you for the presentation. It was really interesting. So a lot of the detection of these internal wave, you base that on Sentinel-1. But as far as I know, Sentinel-1 mostly image the coastal regions and is turned off most of the orbit over the open oceans. How would it be possible to do some of these detections based on SWOT, which I think image a much larger part of the ocean, and have you considered like this limitation of actually not always getting all of the open ocean?
Large internal solitary waves can be seen in SWOT. Even with the smaller resolution, we can detect. We can detect different internal waves with the Sentinel-1 with a resolution of 5 meters and with SWOT with 300 meters of resolution. Sometimes we can have synergies, but yes, it's possible. In SWOT, probably just the large ones, like in Amazon Shelf or in Banda Sea, just for the biggest. But yes, it's possible. The wave mode, the images that we are using in this moment, it's the wave mode that happens normally in the open ocean.
Okay.
There are few regions near the coast. But it's what I try to explain here. We are focused in the wave mode images, but our next step is integrate also IW mode. That is the images that are near of the coast from Sentinel-1.
Thank you. Yeah, I think I missed the wave mode part.
Okay.
Okay.
Sorry,
It
sometimes
makes
it's
sense
not
now.
easy to.
Thank you.
So just quickly to answer your question. So it's not off during Sentinel-1 is not off during the passage in the middle of the ocean. It's sampling on this mode that we're using. And now we started already doing the coastal areas instead of the wave mode, the IW mode. As you say, samples on the coasts. It's a totally different type of image of footprint, but there is not sampled. It's proper. It reads constantly on the coasts, always in the same places. So we're trying to get to use the two modes that operate in the ocean to have full coverage. So this is like a very significant difference, and that's why we're finding internal waves where we thought that they didn't exist, because we're not just studying some areas. So researchers worldwide have been studying certain areas occasionally, and what the system does is treats all areas the same and assesses or classifies every single image that Sentinel produces in those two modes.
Hey, yeah, I had a quick question that just came to mind. There's this PACE instrument that is measuring ocean color. And I was wondering whether that's relevant here in the sense that there may be a signature of these same internal solitary waves in this data set. Is that something that is useful?
There are studies about the ocean color in internal solitary waves, but it's not very clear. Sometimes it's possible to see, but it's really rare in ocean color. I think I'm saying right, George. You agree?